Hello, Shalom. Hello, everyone. I'm so happy to be here because it's good science and all the previous talk was just great. And also I'm happy to be with you guys, the people of Israel, because you can be sure that I am really standing with you. And there's a lot of people with you, and it's very, I mean, this is a lesson for us, how you go through and you're still there. And so I'm very respectful for that. So I'm here also because of my spiritual father. You have, so I have to be. Grandfather, yeah. So, well, I wanted to say a lot of things, but I forgot because of emotion. Anyway, so, yeah, so if it's too long, don't worry, you can go away whenever you want, you know. I will finish myself alone. Maybe Ashley will stay with me at the end, asking one question, so don't worry. So I have a lot of conflict of interest, and I have two startups. More shares than Ashley with Alterity. One developing dopamine into the brain, which is working very, very nicely. So I will tell you something about that. And the other one for ALS with a biotherapy. But today, this is not about that. And I would like each time, because there's some student, to recall what is Parkinson's disease. So I will, because I'm a clinician, I'm a neurologist and a professor of medical pharmacology, so I am leading a big team of research in neuroscience, so I do cell, mice, rats, but what I am good at, it's a very small part, it's Parkinson's disease, and so it's a neuropsychiatric disease, so we are, you know, schizophrenia, Parkinson's disease, it's the same tissue and same problem, neurodegenerative disease. And I'd like to explain what is this Parkinson's disease. And you know, now what is good, well, it's more complex with schizophrenic patients, but we work with PD patients. So they came to the lab, we talk together, we build a clinical trial together, and so people now are really with us. And so when I try to explain what is Parkinson's disease, this is a disease of automaticity. And this is very important because when you talk, when you look, when you say, ha, 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 everything is automaticity. And this is what is altered in Parkinson's disease because of the loop, of the subcortical loop. In fact, when we are a child, we've learned a lot of different skills. And for energy, to save energy, we put in this very small loop of activation of some neurons in order to save time. Because if you start to learn to play piano, the old brain burn because you activate frontal, parietal, etc. And if you look at somebody playing the marvelous music you put at the first place, probably in his brain there's only one or two spots because you have learned and everything is automatic. And this is really important because we will talk about iron, energy. And so to save energy, this is automaticity. And this is terrible. And we need to keep that in mind as a clinician. And it's obviously also cognitive and emotional from the start. It's not just motor. And please never said this is a disease for tremor. We don't care about tremor. This is not Parkinson's disease. We have pathological findings, and all the world is talking about alpha-synuclein, like in Alzheimer's disease, and the dopamine, the deficit of dopamine, and nobody cares about iron. I can tell you about just our club, our family, but about that, nobody cares. But this is really important. And they forget, and I kill every student in the university who said Parkinson's disease is a synucleinopathy responsible for rest tremor. So this one is dead. So Parkinson's disease is a progressive and extensive regulated cell death involving at least dopaminergic neurons of the substantia nigra pars compacta. This is a definition. And then the student, but also the scientist and the clinician mixed up the pathological findings, the etiology, and the physiopathology. Because this is very different. Because they said, well, we don't know why we have Parkinson's disease. We don't know the cause of Parkinson's disease. Because there's no one cause of Parkinson's disease. This is an equation with at least 100x value. And among that, you have, so I take this from the graded risk concept from genetic researcher. you have the frequency, and you have the effect size. And in fact, you can have some very rare monogenic variant that can induce, it's very exceptional, the disease by itself. But you have to wait 50, 60 years. So meaning that age is the #1 risk factor, and also you have, and they forget environmental disease, but Parkinson's disease is an environmental disease. And it's totally related with pesticides. We all know that for many years. So we said, we don't know what's Parkinson's disease. It is pesticides. And all the model of Parkinson, you use rotenone, you use whatever you want. You just have to inject that on the mice, and you have a marvelous Parkinson's disease. So we know that. And the farmer now is recognized and reimbursed. And so if you have a massive intoxication, you trigger a Parkinson's disease. But we are here, all of us, with, environmental small dose of pesticides, solvent, heavy metals. This can lead, after a while, to Parkinson's disease. We will be talking about ferroptosis just after, but the brain, the old brain, is massively accumulating iron, and it's also the lipid is changing. So it's like, I like this idea because I like Australia, and this is like the Australian bush, Everything is ready for fire. So you are aged, and so you're ready for Parkinson's disease with all this trigger. And the people now mixed up this, and the physiopathology. What is the physiopathology? This is how the body is reacting, how the body is competing that. And so they said, Parkinson's disease, this is neuroinflammation. Bullshit. This is protein aggregation. Stupid. This is how the body is reacting and competing, all these aspects for many years. And we know that we start Parkinson's disease after 10, 15 years, where the body is reacting, competing, and all that stuff. And the iron accumulation is part of this physiopathology. So each time they ask me to do any speech in the world, I start with that. Even if I don't have to talk about that, because I'm fed up with, this, with the shortcuts they made to explain what is the disease. Well, now, because of the beautiful talk I have before, I can make my mind shorter, because you know everything about that. Dopamine is in dopamine synthesis, but also this beautiful paper by Dominique Hare from Florida Institute, now is no more, with the metabolism of dopamine. Because also I have a picture of what is the metabolism. And we just talk in the field of Parkinson's disease of catecholomethyltransferase inhibitor and monoamine oxidase B inhibitor, but it's nothing. I mean, the dopamine is mainly metabolized by oxygen, by iron, into dopamine quinone. You recall that just before Evgeny. And so this is really important because, in fact, and the title in the brain paper of Dominique Hare was Dopamine and iron, the toxic couple, which is really interesting because both need them. And though I go fast on that, you all know that it's 20. I said generally 30%, but I think I'm lying. It's 20%. But what is really important, and I love this paper, is a group of Surmeyer. In Chicago, Surmeyer is a major. And he said, well, he studied in the Nature paper, it's a Nature paper, and he studied the dopaminergic neurons that in the substantia nigra pars compacta and substantia nigra pars reticulata. He said, why the dopaminergic neurons? Because we talk about iron, toxicity, pesticide, but the pesticide is all in the whole brain. And was there so specific region which degenerated more? Why is it hippocampus for Alzheimer and the motor neurons for ALS and the substantia nigra pars compacta? And you know the answer? Because they have a hard work. Because it's a pacemaking activity. And Surmeyer did this work on the calcium channel. But he nicely demonstrates that, in fact, it's more vulnerable when it's more active. Which makes sense, in fact, because the hippocampus is always working, how motor neurons for motor activity is a higher consumer of oxygen, and this is like a sinusal nodus of the brain. It's always pace-making the activity for all the automaticity. So this is why this is so vulnerable, and so this is why we need so much iron and oxygen in this part. So now there was, we start, the story, I'll make it brief. In 2004, I saw this beautiful paper of Nathalie Baudart, and this idea, that's why my spiritual father, of the iron. And I saw that we can reduce iron in the brain of people. And I said, I know because there's an iron accumulation in PD, so let's make it simple. I will reduce it with deferriprone. And I start this way, which was stupid, of course, but I was stupid, still there. But I was lucky because while I met Ashley, and this was great because I increased my level in science, and also during this development, right, Ashley, we have this news from ferroptosis coming from the lab of Brett Stockwell in 2012 in Colombia. And so before, everybody was just praying the god of apoptosis. It was always the same fairy tale. And at the end, the cells are dying by apoptosis. Even if there's no apoptosis. They find one caspase somewhere and say, well, you see, it's apoptosis.
You forgot one thing. I reviewed the paper of Stockwell and I sent it to you.
Exactly. Exactly. Another friend as well. That's why since 2012, we started to work on that. So it was so beautiful to find a way that the cells are dying with iron. So, and in fact, this is part of a regulated necrosis. I put this reference from my friend Scott, who's working with Ashley. He nicely put all the type of cell deaths. So this is ferroptosis. And what is good with this story of ferroptosis, he discovers that in breast cancer. But in fact, if you take, I don't have time to go back to the basic, and if in fact, every day there's new paper coming out and new mechanism around ferroptosis. But what is great is when you look at all this mechanism of ferroptosis, it has already been described in the literature without knowing that it was the same picture of ferroptosis. So this iron aspect, this dysregulation in PD, it's well known for very long period. This massive lipid peroxidation, because ferroptosis is defined by iron accumulation and lipid peroxidation at least, which is very classical. We find that in Alzheimer, PD, ALS, stroke, etc. And also what was interesting is that some specific aspect, so there are, if you want to summarize, the GPX4, the glutathione peroxidase 4, is a major antioxidant for lipids, and the XASL4 is also the pro-ferroptotic one that accumulates arachidonic acid in the membrane and renders the membrane more sensitive because of the double bonds to oxidation and to the cell death. And GPX4 was already described earlier that it was also reduced in the PD model. And so we started to demonstrate in 2012 that ferroptosis was really important and pivotal in Parkinson's disease model. And if, okay, that does not want. So that's what we have done quickly on dopaminergic neurons. And yeah, and good point also for the student, the model. Before they used oncogenic model, cancer. And so they wanted to predict what occurs in the brain of people with cancer cells. So what they observed? Apoptosis, never ferroptosis. Now when we take a non-oncogenic cell death, mature differentiated cell death, they are dying by ferroptosis. So that's what we demonstrate. And all the classical condition of PD was triggering ferroptosis, and we show that with lipid peroxidation, etc., and we counteract with antiferroptotic drug, etc., and we published it, this one. And what is good also for the student, that this paper, when it came out, nobody cared. For 1 year, 2 years, for 3 years, and now every day this paper is quoted. I'm on more than 1,000 quotation. So keep on going with your paper, okay? So what is really interesting is that we said, well, the cells are particularly vulnerable for ferroptosis. So we were very confident that the big clinical trial we wanted to put would be successful. And so another PhD, Int, did some work. And so we put just on cell culture iron. And I remember a BioIron Congress when the people were struggling, saying that in fact when you put iron, it's not dangerous for the cells. You need to put kilograms in your cell culture to kill the cells. So iron by itself is not really harmful because the cells love irons. But what was really interesting in the paper we have done here is that when you put small dose of iron, nothing, small dose of arachidonic acid, nothing, and when you combine both, the cells were dying quickly of ferroptosis. And of course, with age, you accumulate iron and arachidonic acid. So the age are preparing the brain. You know, at 100 years, so you have something like 50% of chance of having a Parkinson's disease. This is a natural way out. We all will all have in the best case scenario. Okay, I try to be more optimistic now.
We say 120 years.
Yeah, 120 years, yeah. Yeah, yeah, you're far from there. Don't worry. And so now, and now, yeah, we talk about dopamine, we talk about iron for energy metabolism, and I don't go back to that. But this, you know, as I said, nobody cares about what we are doing on iron and dopamine, etc. And ferroptosis is the gain of interest. But they said, yes, but you need to explain what is the relationship with alpha-synuclein. Because you know, in the PD field, we all pray the god alpha-synuclein. So if it has nothing related with alpha-synuclein, we don't care. It does not exist. So we take back all this aspect. And guess what? Alpha-synuclein is a chaperone protein dealing with lipid metabolism, many aspects of lipid metabolism, many aspects of iron metabolism, and it has its own iron-related element. So this is a master player between dopamine, lipid peroxidation, and so we published this paper with Laura Mahoney, and that she nicely shows that if you increase the level of alpha-synuclein in the cells, you increase you change the lipid composition, and you render the cells vulnerable to ferroptosis. And if you knock out the alpha-synuclein, then you protect the cells, and it has directly related with the composition of ether phospholipid composition of the membrane. So, and also many gene mutation described are related with ferroptosis. So now nobody can say that it's not related with lipid peroxidation, with DG1. I don't have time to go to that, but just to tell you that we are dealing with something very important. And now they said, what is the relation with dopamine and alpha-synuclein? To make it simple, the more alpha-synuclein aggregation you have, the less it is related with PD, because the less dopa sensitive it is. In fact, in some young people, like Parkin or other, have a Parkinson's disease, that's a very small amount of alpha-synuclein. And if you have a very major accumulation of alpha-synuclein, you are almost not dopa sensitive, so it's not a Parkinson's disease, this is a Lewy body dementia. And in any case you can find, you always have an iron accumulation. So it looks like this is more relevant than to talk about ferroptosis and that. And then to finish the presentation before going into the iron chelation, with James Douche, who are also coming from the team of Ashley. And James did this marvelous review trying to explain what this is about between alpha-synuclein, dopamine, and iron. And I think everything is here. It's not totally demonstrated because it has been demonstrated in retina, in other parts. But in fact, alpha-synuclein is dealing with iron incorporation through transferrin receptor. Alpha-synuclein safely make the vascularization of iron, and you need iron for tyrosine hydroxylase and so dopamine synthesis. Alpha-synuclein can suppress activity of tyrosine hydroxylase. Thank you very much. Come with me. And then the vascularization, you have long-term, short-term vascularization, release dopamine in a controlled way, recapture through dopamine transporter, and all this circle is totally controlled. And if you disrupt vascularization with amphetamine, if you disrupt with hyperphosphorylation, if you aggregate whatever, then you disrupt this nice control, and what occurs, you increase DMT1 because you are no more able, using alpha-synuclein, to incorporate safely iron into the body. You don't have no more the safe segregation, so you have dopamine in the cytoplasm, and so oxidized in the cytoplasm. You have iron accumulation in the cytoplasm also because it's no more safely vascularized. And so you disrupt the neurotransmission. So you have a reduction of dopamine transmission and no more recapture. That's exactly what occurs in PD. So we don't have to struggle or to fight each other. If you have an aggregation of alpha-synuclein or if you have oxidation, whatever, this is the end of the story. This is exactly what occurs in the substance nigra of people having Parkinson's disease. So what can we do? You took Spider-Man, I took Iron Man. Well, it was less, you're more original than me. But so what are the rationale for PD? There are many publications showing that it is very effective, whatever iron chelator, in PD. We choose deferriprone because of Yoav and Arnold and Nathalie, and because it can cross the blood-brain barrier. And Yoav, from the beginning, he told me, the first time I saw him, you understand nothing, he told me. That was true. Because he said, it's a redistribution, it's not iron chelation. And I said, okay, so this is why this is good, because this may chelate the iron and give it back to transferrin. We don't know in human, but you demonstrated with you, right? It was you paper, exactly. So thanks to you. No, I really appreciate. And also, I met Michael Spino. It was really funny because he was a big shot of a big, and I was nursing at that time. And I said, can I have deferriprone? Like Amit said, please give me a deferriprone. I want to test in Parkinson's. I said, when I give to you? I said, because I can do it for very low price. And he said, okay. And so he told me from the start, David, there's two problems. You can reduce tyrosine hydroxylase activity. And he told me from the start. And he said, but you know, there's a paper of Waldmeyer, you know? Waldmeyer.
Right.
You should all have this paper if you work on deferriprone, because it explains everything in this paper. And notably also the ICOMT activity. So I answered to Michael Spino, I don't care. I can reduce a little bit the iron synthesis, the dopamine synthesis, because I will reduce massively the metabolism of dopamine through the ICOM activity,
Right.
and through ICOM activity because of the structural of deferriprone, nothing to do with iron, but also on monoamine oxidase B activity, and also on oxidation of dopamine. So I said, I don't care, I will win. He said, well, okay, take the risk. And so I start with a small number, like you will do, monocentric, a small number, just to test it. And I start to, and at the same time, because I'm a clinician, I did it on cell culture and mice. I didn't need it to go to a clinical trial because it was already on the market. But I did it for good purpose. And we did a delayed start paradigm. So 6 months placebo control, and then everybody received the treatment. And we just measure whether it was different. And Ashley just presented this. And so, indeed, we reproduce what has been done in Friedreich taxa to reduce iron in the substantia nigra and the putamen. And what was also very interesting, when we stop the treatment, we have a rebound effect. So it's an active process. But we enroll people within the first 3 years of disease treated with levodopa and dopamine agonist. And also, after 1 month, I say, how you feel? Like I asked the patient, like usual, okay. 2 months later, how you feel? Well, like usual. And 3 months later, 2/3 of them said, I feel better. It's not possible. I don't wait. I don't expect you feel better. Just, you keep the same. And they really seems to feel better. So I start to be like a fool. And so when we published it, we said, that's it. We win. And so this is the concept of Yoav, of redistribution, whatever PD, Alzheimer, rheumatism, inflammation, you have sequestration of iron, and then we can redistribute. We observed in the urine that the level of iron was low, so we don't chelate very much, with 30 milligrams per kilogram per day. And then David Dexter started the same trial later, so I published better. they run faster. And he said in this paper, 20 milligram per kilogram seems to be less good than 30 milligram. So, well, we were very confident. And then we started to discuss with all the experts, the KOL in PD, and said, and at that time it was published that razagiline, the inhibitor of monoamine oxidase B, might be neuroprotective, but we don't know because of the co-treatment with levodopa. And so we decided to go into de novo patient. We said, see, it's pure, and because we were very confident thanks to these two pilot studies. So I received 6 million euros with an application at the age 2020. And we did a simple trial, 9 months. 9 months, why? It's a very slow progressive disease, so 9 months, it's not enough. But you can't, the people can't stand more than 9 months without any treatment after receiving the diagnosis, so they feel really bad. It was a nightmare for several years. I lose several years of life expectancy myself to do such a trial, but we enrolled 372 people, which is huge. So 23 centers all over Europe, etc., etc., etc. And then it was Friday night, and I go out to meet a friend. I have a couple of beers in the center of Lille. And then I have a phone call from the statistician. He said, David, are you sitting? I said, no, why? I'm in the street, I'm not sitting. I met my friend, and so I said, well, you have the result? He said, yes, but you should sit. He said, come on, tell me. I was excited. In just the middle of Lille, surrounded by many people. And I said, okay, tell me 60 years, all the trials are negative, no difference. This is that. He said, no, there's a big difference, but in reverse. So I finished drunk this night because, I was in a misery to know that I find a way to aggravate and to worsen the people. So this is shortly, so we enroll 400, and then during the study, we find that there's a higher dropout rate. So there are some signal, but there is a safety board, independent safety board, they didn't stay to stop. So we move to the analysis. The people were 60 typical people at the time of diagnosis, so very early, They are 60 years old, and they have just, 1 year since the motor symptoms start. So you're very early. And so we never see that with a treatment, just levodopa can do that in the reverse situation, to worsen 9 points, which is huge. So it's not a small aggravation, it's a huge aggravation of 9 points of the total UPDRS. And if you go into UPDRS part 3, it's around almost 6 points. 6 points, it is more than 1 year of worsening. Wow. You can imagine. So now, as we said with Ashley, nobody can say that iron is not important. So we are in the good club here. So you see, we have nice, you never observe that in neuroprotection, never, never. 60 years of failure in neuroprotection, in ALS, PD, Alzheimer, and so they just have to be the opposite. But otherwise, this is perfect. More dropout because the people feel, I can't stand, I want to quit. And so we measure the iron. Obviously, it was reduced, but what was important as compared with what Ashley showed, we didn't have any atrophy so it was even a little, the volume increased a little bit under the deferriprone and reduced under placebo. So we don't know what does that mean, but we didn't have a massive atrophy. On the DAT scan were no difference. Ferritin was reduced as expected, but remained in the normal range, in the blood, ferritin in the blood, and not in the brain, and not in the nucleus, we can't measure it. And the prolactin was 3 times up. And this was a good discussion we have with Scott, right? He said, why don't we look at the prolactin? Because the prolactin, the only inhibitor of prolactin is dopamine. So if you reduce the brain dopamine, you increase the prolactin. So we have the proof that it was hugely, massively related with dopamine. And of course, you can't have 9 points of worsening by the destruction of the brain, it has to be related with dopamine, for sure. So at least we have this. This is why Amit is now so happy and I'm so desperate. And, and so the adverse event agrastosis was not so a problem, not high. It was classical. And I like what you say, Amit, with clozapine, because clozapine saves schizophrenia, but it saves also PD patient. We can just use this.
We give it to
And I gave it every day, hundreds and hundreds of patients. I never had any agranulosis or neutropenia. Anyway, so, but this is not the end of our club of friends of iron, because I have good news. So we, at the same time, Apopharma did 2 trials. One was Sky study. He said, I will repeat what you have done, David, because now I don't trust you anymore. And he keep, because I didn't have the culture of the pharma company. I was a medical doctor. But he said, in a pharma company, you have to deal with a different dose and to prove to FDA that with a lower dose, you can achieve the same level. So, and he said, I love to use the dose according to the weight, because the woman has to be treated differently than men. It's an obvious mistake to treat the same way with the same dose, men and women, and with a big weight or low weight. So we used a calculation according to the weight. But he said you can't do that anymore. So it's fixed dose. And Embark was just to compare de novo patient without levodopa and with levodopa. And so very rapidly, well, that's it. What we observed, we repeat exactly what you observed before. So the Embark study shows that indeed in treated patient, no worsening, in de novo patient, huge worsening. And with a dose, a lower dose than what we were using, with 60 milligram, which is around 15 to 20 milligram, we were, you see here, 4 points of improvement on UPDRS part 3 as compared with 1.3 worsening placebo. But it was only a small number of patients, so it was not statistically significant. So I struggled with the editor to say, well, there's a big signal. Say, no, it's not significant. Yeah, but there's a big, no, it's not significant. So, and at the end, I stopped, and I just published it in Journal of Parkinson's Disease. But you see, there may be a way there with a lower dose. And associating levodopa in order to avoid this drawback effect on dopamine synthesis. So now I try to convince you with different figures, but it's not statistical, but it's close to. So, so the conclusion for PD, I'm not too, no, sorry, it's okay. So I look at Mario, I know the signal. So what can we say? To finish within five minutes? 15, okay. The conservative iron chelation or repurposing the drug or remove the drug and not moving the iron, not remove it, I think we can say that. For everyone, no anemia. And I treat patients for 15 years with NBA, no anemia. So the concept is true. You can't say that. So there's a way to treat people with different conditions with a small dose of an iron chelation. That's very, very important. And we worsen if we don't worsen patient if you have a concomitant dopaminergic treatment, no worsening. And which is good for PD, easy, but for Alzheimer's disease, we can't. We worsen if there's no dopamine, and there's a problem of the dose. The dose was probably too high, and what we observed was at least related with dopamine. Maybe, like Ashe said for Alzheimer's disease, maybe we are doing something wrong with higher dose on mitochondria as well. We don't know, for PD, I mean. So what can we do? Well, I think, and that's my mantra, that this is a compensatory mechanism, as Evgeny recalled, and several people here, that in fact, long time before you accumulate iron, you reduce dopamine transporter to maintain the dopaminergic neurotransmission first, maybe 15 years before the symptoms occur. Then you accumulate iron to increase the synthesis of tyrosine hydroxylase, but it could be bad because you can accumulate iron in the cytosol and increase oxidation and increase ferroptosis. So this compensatory mechanism can also be harmful on the long term. And so I keep saying that, so the compound could be also related to ferroptosis. And you know, this is a story of beta blocker. I keep saying I'm sorry because Ashley and you have listened that all the time, but the beta blocker, when I did my medical studies, they keep saying if you put a beta blocker to people having heart insufficiency, you have 0 to your exam and 0 the next year. Because it was forbidden, because you can worsen the situation. And now you all know that it's the number one treatment for cardiac insufficiency, because they use smaller dose at the time where you have decompensation. Evgeny, you said, when we can measure, or Karin, when we can measure the threshold when iron accumulation in this type of cell or area can become harmful, then you can introduce the drug at a lowest dose. And I'm sure, because of the huge effect, that we will have a huge improvement. And so we will have to do a new trial. Now I'm co-coordinating a large platform of drug assessment, master trial, we call it in France, the same in London. So we checked a lot of different drugs, and I can't use anymore deferriprone because KC does not want. But now I know what to do. I know it has to be at least 18 months because it's a slow disease, a slow progression, same for Alzheimer. We need to associate dopaminergic drugs with a low dose. This one may be good for deferriprone, NAC or NACamide if you have phase 1. Monitor with your fancy new system. We need you, Aviv, as well, to help us on this. And we need to find the drug. If maybe we can buy deferriprone altogether, the club, I don't know.
Is there any company?
Yeah,
so we need
300 shekels. That will be 70 euros, and you get a New England discount. So 50 euros.
No, I'm very serious. We need to discuss about that. Alterity is a small company. I try to help them as much as I can to raise the funds from Cure Parkinson Trust, because this one, as they said, chaperone, because they want to stay away from me with chelation. So they said chaperone, which is true. Ashley shows that. Kajal also is a US company. We don't know where they are right now. Bob Hyder, the one who discovered deferriprone, has also the CN128. But
it's not a good day.
no, I don't know. But we need to have this. So ferroptosis, as I said to you, is very important to consider when we talk about iron. I think it could be the missing part explaining all the relationship between the key pathological findings we have, iron, dopamine, synuclein. And also this is very interesting for ferroptosis because you can have biomarkers with MRI, because if you said if you increase iron, you can say in a certain way you may have ferroptosis, and you can also use with PET scan or with Foricini or malonaldehyd measure in the blood or in CSF that there's lipid peroxidation. And so he said if you have both iron accumulation and lipid peroxidation, said ferroptosis is occurring. So you can prepare some stratification for patients to be enrolled. And so now all the people in the world love ferroptosis and said we stay away from iron accumulation and we go for ferroptosis, which I think we should do both. For antiferroptotic drugs, but we need to keep iron chelation, I think. And I'd like to finish by something. So before saying thank you to everyone, I'd like to say that I'm not just doing something to worsen my patient, so I want to so that I will never be invited anymore in Israel. So I just want to say that I do something good. I did something good. I just published in Nature Medicine that we have developing also just to help people. And I had the same idea at the same time of iron chelation. So we put a pump here, you see. It's a pump already in the market, a small catheter, and we put in the third ventricle here. And we infuse dopamine. Why dopamine? Because when you give a listen, sometimes I have a student raising the hand. Sir, why don't you put directly dopamine in the brain? Yes, boy. Why? Why nobody did it? And in fact, somebody did it. Stanley Fan But the problem is dopamine, when you use dopamine, it's oxidized very rapidly. So it turns black. So when you use that in rats and monkey, I will send you the paper. The Yebenez did that, a postdoc Spanish postdoc in US, in Colombia. And he killed the concept. And so for everyone for 60 years or 50 years, they said, it was, 60 years, they said, well, we can't use dopamine. It's oxidized, dangerous. So it was a dogma, like apoptosis. And we have to fight in science against dogma. And so because I'm stupid, I said, my postdoc keeps saying to me also on mice, he said, David, it's turning black, it's turning black. I said, I'm fed up with you, Charlotte. If it's turning black because of oxygen, you should put it without oxygen. And I turned to my friend and said, how we can do that without oxygen? He said, well, I don't know. Maybe a chamber when we do some bacteriology. And I said, well, let's do that. So the following week, we prepare dopamine without oxygen, and we inject. It massively works in mice and rats and monkey, and then we created a startup, and then we did a trial on 12 people. And it's hugely efficient. It's really, really safe. And this maybe become the backbone therapy if I succeed raising 50 million euros. So there is some pots at the end, so if you can put some. So I'd like to thank you very much, all the iron lover. Of course, this is the Fairpark 2 team. They never came back to Lille, I don't know why. And my team in preclinical and clinical setting. My spiritual father, I don't know if I should say that because it was a bad idea at the end, so I don't know. No, Ashley, it was quite the same age, right? Scott, James, David Dexter, this was a photo last night. And to finish, you see, when I just arrived in Jerusalem, which I love more than ever, this black iron post was there. So maybe this is the future. Thank you very much.